And now, finally, the distribution you've all been waiting for, the geometric distribution. This is the fourth and final installment of Chapter 8, so enjoy it. So let's talk about what a geometric distribution is. There are 4 conditions that be met. It must be success or failure. Sounds familiar. Probability P is the same in each of the observations. Sounds familiar. The events are independent. It almost sounds like binomial, except for geometric is failure until first success. Failure until first success. It doesn't say any success, it says first success. So write down these 4 conditions, and we'll go on. So here's the probability. It says if x is equal to n, and here's what it is. And it's q to the n minus 1 times p. We'll talk about how that makes total sense here in a minute. Here's the example. A free throw shooter has a 0.7 chance of making the shot. What is the probability the first free throw is made on the 3rd shot? Okay, let's see if this meets a geometric. So you verify these 4 conditions, and I'll wait for a second, and then once you've verified them, we'll talk about it. Is this a success or failure situation? Yeah. Either you make it or you don't. So let's write that down. So you either make it or you don't. Make the shot or not. Is the probability the same for each observation? 0.7, yes. Independent, it doesn't say that it's independent, but it doesn't say that there's anything that influences it. I'm going to assume independence, but if you want, we can put PWC. And remember, that's proceed with caution. And is it failure until first success? Let's see. The first free throw is made on the 3rd shot, so it's failure, failure, success. So yes. So let's see if it makes sense just from a probability standpoint. So the probability you missed the first one is 0.3, right? Because your probability of success is 0.7, which means your probability of failure is 0.3. So we have to have a missed shot followed by a made shot. And that looks like 0.3 to the 2 times 0.7, which is exactly what we said up here. Q to the n minus 1, and n is our sample size, which is 3, times p. So let's use the calculator again to out. So we have 0.3. Let's try this again. 0.3 times 0.3 times 0.7, and I get 0.063. Okay, so there's only one more thing to talk about, and that's the expected value and the variance, or standard deviation. So here's the formula for it. And then here's a practice problem, and we'll talk about this. So I'll let you pause the video, and we'll also talk about, and I want you to think about this. If I give you the variance, what's the standard deviation? Okay. So you should have been able to write this. I hope also what you've done is you've solved these 2 problems. If not, go ahead and do that. And while you're doing that, I'm going to solve for the standard deviation. The standard deviation of x is the square root of the variance. So in this case, it's the square root of q over p. And if you don't know how it changed it, I want you to take the square root of this and then stop and think about for a second how I got from here to here. Square root of p squared is p. There you go. How many times do you expect to flip a coin until you get tails? That's a good question. What's the probability of success here? That's 0.5. Probability of failure, well, that's also 0.5. And that should be everything for my shopping list, right? How many times do you expect to flip a coin until you get tails? So it's 1 over the p-value, right? And to simplify this, I'm going to multiply the top and bottom by 2. That gives me a 2 on the top and a 1 on the bottom. And that's 2. So I expect to flip a coin 2 times till I get tails. Okay, so what's the standard deviation of this? So standard deviation is the square root of 0.5 divided by 0.5. And let me fix that, make it look a little nicer. There we go. And I'll use my calculator here that I have off to the side to calculate this. So square root of 0.5. I get 0.07. Let me write it like this. 0.707 107. And then divide that by 0.5. So I get the standard deviation of 1.414. That's it. Actually, geometric is pretty cinchy. So cinchy, even Mr. Hampton can do it. Okay, I hope this helps you a little bit. Please make sure you do your homework so that you can solidify these concepts.